Hey, hi. How are you, Ahmad? Nice to see you back. Nice to see you back. You were away last time. Hope you're watching the recorded one, huh? You do? Okay. Um, all right. Yesterday lecture was about the equilibrium of rigid body. So, what difference is between a rigid body in equilibrium and a particle in equilibrium? All right. So, I have to introduce a very important concept, and that is called system of concurrent forces. Concurrent forces. So, if this is a rigid body, I mean, we generally draw the rigid body like a potato. It could be any shape. I mean, this is just a two-dimensional. If you understand two-dimensional, you understand the three-dimensional easily. Okay. So, with this shape, arbitrary shape, imagine this is a piece of cardboard. You want to fix it on the wall. All right. So if I apply a couple, what happens? If I apply a couple, you remember the definition of the couple. Couple are two forces uh, of equal magnitude, opposite direction, right? So that couple is two forces equal opposite direction, but they are a little bit distance between them. And that distance is responsible for what? Making that rotate. Does this one rotate clockwise or counterclockwise? Counterclockwise. Can you see that? All right. So can you imagine this is a cardboard you put on the wall, and then you are applying two forces. The don't forces don't collide; they are parallel. But if I put a tack pin here, I add a tack pin. You know what tack pin is? A pin. And just by pin, I fix that to the wall. That tack pin could be everywhere. Could be in the middle, could be the corner. But because this is one point, there will be a rotation. The system is going to rotate, and that would rotate counterclockwise. All right? So imagine that I'm reducing that distance little by little, and eventually, if I bring that force from here exactly collinear with that, or in another word, if I make the distance between two forces zero, so mathematically we know, mathematically that is m or couple is equal to F times D. And mathematically, if I put D equal to zero, that means there is no couple. All right. So you remember from energy and motion, the conditions of equilibrium. There are two conditions: condition of rotation, condition of translation. All right. Okay. Now we have the very um, good student of the class, Porty, joining us. I simply recap for him. So this is Porty what you missed. All right. So I was talking to the class that a rigid body is a system of parallel forces of same magnitude, opposite direction, right? So here, that's a rigid body, and that rigid body is subjected to two forces parallel opposite. So two conditions for equilibrium. You remember from high school. You remember that from the energy and motion. So the conditions class from classification point of view, one condition is system can rotate, which is due to the couple. The other condition is the system does translation. It goes in X and Y direction, right? So if you ensure the system doesn't translate, doesn't rotate, the system is in equilibrium. So a bridge, you're making a bridge, you don't want the bridge, you want the bridge to behave. If the bridge rotates, the car would collapse. If the bridge translates, that's not good. So you want to fix it from translation rotation. All right. So what is wrong with this system? This system, from translation point of view, it doesn't translate because net forces in X are 0, net forces in Y are 0, isn't it? But from rotation, this system is not at equilibrium because the net moments are not 0. Okay, so that is something easy to visualize. It's a piece of cardboard I put on a wall, and then I put a tack pin, and then I apply two forces which have a distance. The system is going to rotate. That means the system is not at equilibrium. Now, mathematically, I say couple is equal to force multiplied by this. I hope you remember that from last week. Couple is force multiplied by the distance. So mathematically, if d becomes 0, couple is 0, isn't it? So, but how does it is interpreted physically? Physically is if I put d equal to 0, that is to put the forces head to head. When the forces are head to head, we call them collinear, right? And then this object or this rigid body, I want to give this a name. What do I call this? I call this a two-force member. All right, a two-force member, or in short, we call this 2FM. Two-force member. This is a two-force member, isn't it? Now, I want to give you a recipe. A two-force member, when a two-force member is at equilibrium, when the forces are collinear. The only situation a two-force member can be at equilibrium is when the forces are collinear. They have the same line of action. If I draw the line of action of this one, I draw the line of action of that one, they coincide, right? So let's memorize this recipe. A two-force member. From now on, two-force member is a very important family of the structures. So to be honest with you, between now and end of semester, you mostly are dealing either with a two-force member, three-force member, or you are dealing with the beam, which bends. That is a complex structure. But this structure, when we are referring to a structure in this subject, the most important family members are two-force members, three-force members, and beams. We don't deal with the shaft. We don't deal with the, I don't know, other columns. We only deal with the, and then this shape, that potato shape, shouldn't fool you. I mean, it could be something like, if I have a boomerang shape object, you know what boomerang is? Okay, so this boomerang has two exertion points here and there. All right, so this, if this is a two-force member, it means only two forces are applied here. Can I have a situation like this one and that one? Can you imagine this system of forces to be at equilibrium? No, because unless the forces are 0, these forces are not collinear. When they are collinear, okay, to make them collinear, first you need to know the line of action. From here to here, this is the line of action. That's the only scenario these two force member can be at equilibrium. You need to have either forces pushing or pulling, but because this is classified as a two force member, the conditions, well, condition of translation, condition of rotation. Translation is when net forces in X and Y are 0. So I take my X-axis like so. This is my X-axis. So net forces along the X, F minus F, 0. Net forces along the Y, there is no force there, so net forces at Y is 0. So translation-wise, the system at the equilibrium, and rotation-wise, that is 0. Why? I told you, couple is force multiplied by d, and when d is 0, d is the distance between two parallel forces. If D is 0, couple is 0. And then you just want to visualize it. That's a cardboard. You put it on the wall and put a pin wherever you want, and then attach to a string to that pin. Pull it from both sides, push it from, it won't rotate, and it won't translate.
The forces are not equal.
Yes, equal. Yes. Equal opposite direction. So two force member, just remember, because later we introduce a structure which is constructed by rods. Rods are pinned together at the end. That is called the truss structure. Truss structure, everything is composed of the two force members. And when you want to find the forces in individual bars, you have to assume that bars are two force members. The forces, in another word, a two force member can only become longer or become shorter. Can you visualize that? So this, when this becomes longer, when I pull this under tension, it becomes longer. When it becomes shorter, when I push this, it becomes shorter. If I try to bend it, that's not a two force member. Okay, so don't let that rigid body shape fool you. That potato, it could be any shape, could be a boomerang, but generally speaking, when we say two force member in the truss structure, they are straight, they are like bars. Have you seen bridges? The bridges are made of bars which are pinned at the end together. Okay, so those are two force member bars. Okay, so hopefully from now on we repeat and repeat and repeat about the two force member such that it becomes crystal clear for everyone. But maybe a little bit more tricky, that is when a rigid body has three forces. Okay, three forces, I need to introduce what is called system of concurrent forces. Concurrent is a very scary, hairy word. So what concurrent means? It means few lines, they are colliding at one single point. That is concurrent. So here, no matter how many force I have, so again, my rigid body is represented by a arbitrary shape. How many forces are here? More than two. Could be three, could be four, whatever. So if there are more than two forces, the condition for equilibrium is if I extend that and extend this one, they collide at this point, right? Any other force should also pass from this point for this to be equilibrium. So if there are no matter how many forces, all these forces should pass through here. So this is called a concurrent system of forces. It means all forces are colliding at one single point. And if this one, for example, one of the forces is not passing through that point, if only one of them is like so, this system cannot be at equilibrium. Maybe from translation point of view, it is at equilibrium, but from rotation point of view, it keeps rotating. What is the use of it? What is the use of it? Okay, I tell you what the application of this. Why did we bother to such a complex definition? The reason is if my object is subjected to three forces and the object is under equilibrium, I only know the direction of two of them. The third one, I know the magnitude, but I don't know the direction. So I can assume because this object is at equilibrium, the third force is passing through this point. It has to be with that direction. Otherwise, the system is not at equilibrium. So by knowing two forces, you find the colliding point. The third force should pass through here. If I have three forces, the fourth force, I have one point here. That force should be in that direction. Otherwise, the system is not at equilibrium. So this is the application. We put that in practice soon with some good examples. All right, so I mentioned rigid body. Rigid body versus what? Rigid body versus point. In energy and motion, yes, you might have dealt with a hammer, with a car, with a box, but over there, everything was lumped at the center of gravity. We pretended that this is represented by a single point. So the mass is lumped at the center of gravity. If that's an airplane, yes, all the mass properties are lumped at the center of gravity. Yes, you are analyzing an airplane, but you're assuming the forces, the gravity, everything is at the center of area. But here, that's not the case. Here, when we say a rigid body, yes, the rigid body, yes, of course, it could have a weight, but then the forces are distributed. The forces could be everywhere. And to keep that under equilibrium, either they become two force member, three force member, or even more complex, even a beam. Later on, we introduce a beam. All right. So these definitions, it's hard to find them classified here and there. So these are more important than the solution and number. So once you know these things, it helps you to understand, solve the problem easier. Okay, so now we start with page 172 to 173. All right, these are the review problems. And okay, let's try the first review problem. All right, here that is a boom, and the total length is 9 meters. And well, the weight of the boom is 4 kilonewton, and center of the mass is not right in the middle. That is at point G. It means the boom is not have a uniform cross section. But then a motor is exerting a moment of 30 kilonewton in the clockwise direction. And for this system to be at equilibrium, what is the maximum weight of the person who is sitting there? Okay, that person is 6 meters away from the tip of the boom. So if I want to zoom in here, maybe you can see that better. You see, the boom 4 meter ends here. After it ends at the end of the 4 meter, so here maybe that's not very visible. That is the end of the boom, right? Between the end of the boom and where the man stands, there is a 0.6 meter horizontal distance. So for finding the maximum capacity, what is the heaviest person, the most obese person can stand here and still the system doesn't topple or rotate. Okay, obviously you need to have the rotations balanced. So there is a rotation due to the M with respect to point G. With respect to point G, the rotation is M, and that is negative M. With respect to point G, what is the rotation? Let's bring all the rotational effect at one single point. You remember we did that practice in week 2. We tried to lump all the forces rotation at one single point. So rotation is a free vector. Slide it wherever I want. So M, if I bring M here, there would be no penalty. If I bring M here, no penalty to bring M from here there. M can freely move over the plane. 4 kilonewton, I don't need to move it. I keep it where it is. And then I want to bring W to here. For that, I have to pay a penalty. How much penalty I pay? The penalty I pay is I put W right here, and the penalty I pay is the product of W by the shortest distance between that point and this line. So what is the distance between that point and this line? The shortest distance between G and here, that is this length. How can I find it? That length is 0.6 plus 5 cos 60. Everyone agrees? Cos 30. Yeah, cos 30. Thank you for that. So, and then that would be in this direction, right? This is W multiplied by 0.6 plus 5 cos 30. All right. This is M, W, and this one. So I need to set everything equal to 0. That W of the beam doesn't make any rotation because that is passing through here. So M is minus M, and this one is positive, plus W 0.65 cos 30 equal to 0. These two should cancel each other. Yep.
Yeah, why is the penalty for
W is this is like a parameter. You want to see what is the largest capacity of the. So what is the heaviest person can stand there? What is your question again?
Now you got the M was G, but W you didn't indicate.
Yes, that has to do with week. I think week 1. At the end of week 1, I gave you two scenarios. One scenario was a person is holding a rod, and here someone is holding a rod with their hand. So if this is equal to the very same system F being shifted from here to the beginning of the rod, you don't pay any penalty. This is like you're holding the rope. It doesn't matter where this is being pulled, right? So we say if the force is shifted along the line of action, no penalty. But imagine with this shape, if I did have someone sitting at the end of this rod, all right, this is making a large strain on my wrist. I'm holding someone, and then if I bring that one here, these two systems are not the same. I have to pay penalty. The penalty I pay, I bring the force here, and the penalty I pay is I add a rotation of, if this is D and this is F, that FD is the penalty, the rotational penalty should be added to that. So the very same thing we did here. Here, I'm trying to shift W from its line of action to another line of action. How much I shift that? The shift is 0.6 plus 5 cos. That's how much I shifted. And what is the force which I'm shifting? The force W multiplied by that distance. That is how much penalty you pay. And then W also should be included there. So just memorize this as a recipe. When you are shifting a force normal to its line of action, you shift the force, you put it at the new point, and then the penalty you add is a momentum, which is equal to that force multiplied by the shortest distance between old position, new position. All right, and then in this problem, we have been given M, and M is 30 kilonewton meter. So if you include minus 30 plus whatever, and once you find W, the unit would be in kilonewton, would be 30 divided by 0.6 plus 5 cos 30, and whatever you find, that is in kilonewton. Because m tends to rotate the system in one direction, and that weight is making the system rotating positive, negative, positive. They have to cancel each other. That is a sign convention. If you want to use the right hand convention, m is right hand, is u is a minus k, and with this force coming here that's projecting out of the plane, that is positive. Counterclockwise, clockwise, negative, positive. Practice. All you need is just more practice. Don't worry, this is not that complex.
So, and why the distance should be 2.6?
Why?
Why distance is 0.6 plus 5 cos?
Okay, because what you care is the shortest distance between two lines. Do you remember from geometry or whatever you did in high school? If I give you two lines, so this is line number 1, this is line number 2. What is the distance between them? So you could say that is distance. This is not the distance. The shortest distance is when you draw a normal between both of them. So this is that's it. And also, if I have a line and I have a point, what is the distance between that point and this line? That is not the distance. This is not the distance. The distance is when you plot the normal to that line. This is the shortest distance. And here, what is the shortest distance between W and G? Both of them are vertical. 5 is not a vertical size. 5 is a inclined.
Yeah.
You have to project it. But 0.6 is normal to that. So 0.6 plus the horizontal component of 5. 0.6 is offset. That's it's at the end of the beam. You have a little offset. This is 0.6. From here to here is 0.6. It's not directly connected at the end of the boom. It is just projecting a little bit to the left. 0.6 in horizontal direction. What is available? Diagram?
Yeah, that's what you wrote and everything.
You mean the one which I?
No, right now what you did. Yeah, you're talking about the whiteboard. Yeah.
This one?
The whiteboard. No, what you just did. Yeah. No, the sketch there.
Yeah.
Will it be made available in the mountain?
Yes. Hi, Niju. All right. So let's go to page 195. Okay, 195, we have of different problems. Just maybe we start from something simple. Okay, we start from something simple. Agree? So free body diagram. What is free body diagram? So free body diagram could be your best friend or your worst enemy. So maybe this doesn't have clear images. I make a more resolution. Okay, so this is more readable. 195. All right, now let's make a free body diagram for this one. I know you've been told about the free body diagram in high school or in energy and motion, but based on my experience, that is something a little bit difficult for a student to digest and understand. What do we mean by free body diagram? So free body diagram is a virtual envelope. This is a virtual envelope. This is a part of the universe. You decide to visualize an envelope inside the universe. Anything goes inside the envelope, that is free body diagram. Anything stands out, that is universe. You only concern about what is inside the envelope. The envelope is not visible, it's just in your mind, okay? But it has to be a closed envelope. And who decides about the choice of envelope? I mean, here, if I want to make an envelope between here, let me pretend I want to make my envelope here. Is this an envelope? Anyone can see. All right. If I make this one an envelope, what happens? This envelope, what goes inside? That's a portion of the rope. And this rope, from yesterday lecture, which was recorded, hopefully, I hope you have watched it. Otherwise, I'll be talking blah, blah, blah. All right. So I made that envelope, and then by doing that, my envelope would cut through the object. I need to scissor that one from here, that one from here. And when I cut, it's going to bleed. The forces are hidden, the force become visible. So here I will have the forces exposed at both ends of my rope. That is the first free body diagram. But if I decide my free body diagram to be, so if I decide my free body diagram a little bit larger, if I take this, my free body diagram here, that's a virtual envelope. And now I'm releasing my beam from its left support A, from right support B. And what it makes is, then my free body diagram would be what is inside the envelope. A, that is a pin. How does a pin prevent my system from movement? It only resists against the horizontal movement, vertical movement. So what is hidden after you're cutting and releasing it, that becomes visible. So you put two reaction forces wherever you find a hinge. It means your hinge can resist against the horizontal movement, vertical movement. It won't resist against rotation. So that's why I didn't include a bending moment or torque. So what about the, I'm releasing that cable. Cable can only apply forces parallel to its direction. All right. So with this one, my free body diagram would have a force at the direction of 3, 4, 5. All right. And now you have to solve. This is free body diagram. So don't worry about this problem. Just listen carefully. Free body diagram is a virtual envelope. Depending on the circumstances, you decide how to visualize that envelope. And when you visualize, what happens is you are taking that part of the universe away. Imagine you are doing a heart surgery. You are doing a heart surgery. The heart is connected to the rest of body by 2 veins. You want to bring that out and study it in the lab. So you have to cut the veins, otherwise you cannot bring it out. And when you cut, what happens? From the vein, you get bleeding out. So whenever you're releasing a portion of the structure, bringing that in your free body diagram is like your laboratory. You want to study the forces there. So you grab a portion of the universe, call this isolated system. That system you isolated inside the envelope. And in isolating means wherever you did the cut is bleeding, you include the forces there. Before you cut, the forces are hidden, they are not visible. Once you cut them, you have to expose them in your laboratory, right? This is like you're bringing the heart there for heart not to die. You need to keep feeding blood into it. And feeding blood means you expose those forces over there. So from now on, we have to make a decision about how to make free body diagram, and that is a strategy issue. From problem to problem, that is different. Free body diagram is your best friend, your worst enemy. If you practice enough, you know how to make free body diagram. If you don't practice, you find it very confusing. All right. So here in this problem, I mean, the knowledge which I gave you at the beginning of the class. I told you about the 2 force member, 3 force member, rigid body, and here, that free body diagram, this becomes a 3 force member. All right? So 3 force member means eventually, all right. And then, by the way, in making that envelope, I'm missing something. Anyone can tell me what is missing from, I made 500 is missing. Yes, thank you for that. So this is not a 3 force member now. So don't worry about the concurrent forces. If that was 3 force member, we have to find the intersection of the forces where all forces are colliding. But here, all you do is you apply the condition of preventing rotation, preventing translation in X, preventing translation in Y. That is net forces X equal to 0, that prevents this from horizontal translation. Net forces vertical equal to 0 prevents this from vertical translation. And net rotation about any point equal to 0, it means my system won't rotate. 3 conditions. But we just get into that later. For now, only think about the free body diagram. Want to know how to make free body diagram. So first, I told you if I'm making my free body diagram, my envelope is here. How many cuts do I need to make? 2 cuts at the top, at the beginning. And by doing that, the cable becomes a 2 force member. Remember, I told you 2 force member only is at equilibrium when the forces are collinear. That's why in that free body diagram, I made the forces collinear. Otherwise, my rope is going to rotate. It never can be at equilibrium. If I make my free body diagram like so, how many cuts I make? I make a cut at B, I make a cut at A to isolate this from universe and put it in a lab. The lab is free body diagram. We want to study the forces. Let's do some more exercise. Okay, let's have a look at this one. We want to make a free body diagram of that. Okay, with this system that is attached to the universe, you cannot study the forces. How do we take that to the lab? The lab is called free body diagram. We have to release the support. So just a bit of advice. In the yesterday lecture, recorded lecture, hopefully you had the time to watch it. If not, the most important thing is supports. So how many supports type do we know? There is one kind of support called hinge. This is a hinge. There is a support called roller. If there is a roller, the roller can resist against the normal forces, but it doesn't resist against the tangent direction. So only the roller supports develops one resistance, which is normal to the interface of the object. Hinge. Hinge is a kind of support in 2 dimensions. The hinge prevents from X movement, from Y movement. It doesn't resist against the rotation. So if I want to release the support, I need to include the proper type of bleeding. If I take my visual or virtual envelope like that, I want to isolate this one from universe. How can I isolate it? Okay, that's how. So I made a cut through here, and I made a cut through here. That's how I isolate it. So here, because I released that from a hinge, hinge is resisting against the horizontal, vertical. I include 2 forces. Here, I release this against the roller. The roller can only resist against the normal movement. And what other forces did I miss here? At the moment, I didn't include in my free body diagram. And then weight is always included in the free body diagram unless it's being neglected. If the problem specify to include the weight, and then the other situation is if that structure is laying down horizontally, the weight doesn't come into free body diagram. But if that's being hanging vertically, the weight is included in free body diagram. But if the problem is silent, if they don't give you any number about the weight, that shouldn't come into free body diagram. So let's go to another example of free body diagram. All right. So this one, it has what is called a distributed force. Don't worry about that. We include that later on. Let's take this one. All right. All right, so this is attached to the board. I want to study it, have to make a free body diagram, to release it from the board. And how many supports are here? One hinge, one roller. Okay, so that is my virtual envelope. I release that from the universe. Anything inside the envelope is my free body diagram. Anything outside the envelope is universe. You don't care about it. And how many incision or cut should I make? I have to cut it from here, cut it from there. So in that, when I release it at A is a pin support. It resists against the horizontal vertical movement. So I include two forces, AX, AY. And B, just that is when you might get confused. When I say roller, what you do is interface. What is the interface of the roller and the beam? This is the interface, right? So this is the interface. Interface, that interface is if the roll is gonna slide, that's the path of sliding. Always you have to visualize the path of sliding, and then your force would be normal to that path of sliding. So including the force should be placed normal to that. So this is path of sliding. The force is normal to that one. That is how roller is.
Can we put another arrow in the opposite direction?
Here?
No.
Yeah, one arrow is there. That's external forces. External forces we always include.
Towards the roller, can we put another arrow?
Roller is here.
Yeah, can we put another arrow that's opposite that direction?
Here?
Opposite of that one.
Well, that is a good question. It is free to separate. So that's not the direction of resistance. Unless you have one kind of roller which is called a guided roller. If guided roller is confined between slots, so the pin can move inside the slot, it cannot go up, cannot go down. In that case, the normal could be either this way or that way. But in a situation like that, if the force is opposite to that, it's going to release. I mean, this is an action reaction. Okay, so that is how much force is being exerted by roller to the structure. So a structure applies the force to the roller in a reverse direction, but because this roller is one directional, we know the direction. If that was a slot, we didn't know whether this is going up or down, right? So that is, I call this FB or NB, N normal B, FAX, this is free body diagram. Let's go, no question. Can we go to the next one? All right, let's try the middle one again is a distributed force. I mean, I can leave distributed force as it is. And another type of support which I didn't mention, that's called cantilever. Cantilever, you know what cantilever is? Or fixed end. Fixed end is like a truss. Have you seen the truss structure? That is a horizontal structure. From one end is fixed, it doesn't rotate. It doesn't translate, doesn't rotate. So here at A, I have what kind of support I have over there? That's a cantilever. Well, it's not a full cantilever. It is free to slide vertically, so I don't include the vertical reaction. But horizontal reaction I include, and also the rotational resistance, I put a resistive torque over there. And what about B? B, if I want to find the direction of force, first, let's find out the direction of a sliding. Direction of a sliding is horizontal. And how does it resist? Normal to the sliding. So let's try this one. We want to make a free body diagram of that one. All right, so here, my envelope should release this from B from C. So that is my envelope. And at C, it's a pin. It won't offer any resistance to our rotation. So no moment at C, only two components of reaction, horizontal, vertical. We call them CX, CY. What about B? B is free to slide horizontally, that's a tangent, restricted vertically. So my reaction would be vertical to B and pointing up. And this is external force. External force, weight, they're always included in the free body diagram. Let's go to next slide. That is page 196. 196. Okay. Okay, can I get, because this is a tutorial class, can I ask you to have a thought about this problem for a few minutes before I give you the solution, or we solve it together? Before that, I want you to think about that and see how much you can apply the discussion we had to this problem. 5 minutes is fine. Everyone want to give it a go? wonder if I shared the correct screen with you. When I annotated, did you see my screen? There are two screens here. It seems you are looking to my. Yeah, that's the right screen, is it? Yeah, that's the right screen. All right. So here we want to make a free body diagram of the structure. So I want to release that structure and bring that into free body diagram. How many releasing points are there? Two. I have to release it from A, I have to release it from B. And A, what type of support is classified? What? Pin. And pin, how does it resist toward the movement? Only translation. So it prevents horizontal translation, vertical translation. So if you release at A, you expect to have, well, first of all, that is my envelope. This is envelope, two cutting points at A and B. We are releasing at A and B. A is classified as pin, and pin offers only horizontal, vertical resistance. And then B. B is free to slide horizontally, but is restricted to move vertically. So that is the tangent or sliding direction. Normal to that is wherever the rotor support resists. So that would be like so. And then I make sure everything else is included. So there's no mention of the weight. I don't have to worry about the weight. Also, I notice there is a coup or bending moment at the right hand side. This is 3 kilonewton meter, which tells me I need to keep the units all in kilonewton, or I have to convert this one to newton. As long as you are consistent, that's fine. And what else? That 5 kilonewton, I can include it as it is, or can be resolved into two components, horizontal, vertical, right? Resolved into two components, 5 resolved vertically is 5 multiplied by vertically. That's multiplied by 4 divided by 5. That is 4. And 5 resolved horizontally, that would be 5 multiplied by 3 over 5. This is 3. And then simply I include the forces with the right symbol. That is, I call this AX. From now on, that kind of labeling is very common. For pins, we use AX, AY. Here, that is simply BY, or you can say NB, something like that. Okay, so when you are dealing with a free body diagram, it's important to know if that is solvable. And then solvable from mathematics, specialist methods, whatever you completed during your VC, there are 3 unknowns. You need 3 equations to solve. So these 3 equations, equation number 1, that is the net forces horizontally equal to 0. The second condition is net forces vertically equal to 0. And the third condition could be net rotation with respect to any arbitrary point. Could be point A, could be point B, could be any point. If a system doesn't rotate, it doesn't rotate with respect to everywhere. So we just have to be smart to take the point of rotation to be more convenient. So here, with any point equal to 0. Starting from the first conditions, how many horizontal force are there? So that is plus AX plus 3, that's it, equal to 0. And therefore, I find AX is minus 3 kilonewton. So what does it tell me? It tells me, look, when you are assumed direction of the reactions, you should have taken it in opposite direction. That's okay. We always start with an assumption, and then once you solve, we find out how to fix that assumption. Vertically speaking, second equation, how many vertical forces are? Plus AY minus 4 plus BY equal to 0. So this equation cannot be solved at this stage because it has two unknowns in it. Maybe before solving that one, we go for solving the third equation. All right, third equation, this is like an exciting computer game. So you have one bullet. With that bullet, you want to kill as many people as you can. And if I take my center of rotation here, that is, I'm shooting at this point. So from rotation point of view, if I shot at this point, the rotation of 4 kilonewton is 0, rotation of 3 kilonewton is 0. If I shot my bullet here, that would make the rotation of By with respect to that point 0. If I shot it at here, or if I choose my point of rotation here, there. These are like, you are making decisions, and that decision could make your solution easier, can make your solution more difficult. What is the most smart point of rotation here? B or A, they're the same. Both of them. If I take it at B, then I don't have to worry about the magnitude of B because that won't make any rotation. I want to write a rotation equation. In writing that rotation equation, I have three options or many options. I can take point of rotation here, can take it here, can take it here, anywhere I want. But what are the consequences? If I take my point of rotation here, I don't have to worry about the magnitude of AY, AX because they won't make any rotation. If I take my point of rotation here, in my rotational equation, shouldn't be worried about magnitude of By because that won't contribute toward the rotation. Is that clear to everyone? Do you need to explain more?
Also, wouldn't it affect AX because it's still going directly into point rotation?
Well, if that is A, both AX, AY.
If it's at B, AX is still facing directly into point of rotation, so you don't have to worry about AX either.
Yes. This would help to, if I take it at B, you said?
Yeah.
If I take it at B, that would vanish BY rotation. That would vanish AX rotation. If I take it as A, that would vanish AY rotation, AX rotation. All right, so I think either point would serve the same ease. So let's take that one with respect to point A. If I take it with respect to A, these two rotational effects would vanish. And also rotation of 3 would vanish. Because I assume there is no specification about the thickness of the beam. If thickness of beam was given, then that force projected here would make a little bit offset, would make the rotation. But now we are assuming this point is sitting right in the center of the beam. So because this is at the center of the beam, the 3 kilonewton is passing through A. It won't make any rotation. So that is 0 plus 0 plus 0. And then how does 4 with respect to the A makes rotation? Does it make a clockwise rotation or counterclockwise? Clockwise. So that is negative, and the magnitude of rotation is 4 multiplied by the distance. What is the distance of 4 to point A? 1.5. So that is minus 4 times 1.5. And what is the rotational effect of By with respect to the A? Is that clockwise or counterclockwise? That is counterclockwise, is positive. And that is By multiplied. What is the distance of B to A? 3. And am I missing anything? Should I include something else? This is a rotation equation. The external 3 kilonewton, is that positive or negative? Negative. So I put a minus 3 at the end, that is equal to 0. Question? Again, explain. All right. So I started with the condition of rotation. That condition of rotation, you have an option. You can take point of rotation any point you want. So you want to use your decision in a smart way. We could take point of rotation point A. If I take point A, this is like you have a grandfather's frame, put it to the wall, you only have one tach pin. Tach pin, you put it here. Now, these two forces, tach pin is here. Do they make any rotation? No. What about this point? Does it make rotation? This is almost here, that passes through here, won't make any rotation. But this one does. This one rotates my frame that way. How does it rotate? 4 multiplied by 1.5. What about this force? Does it make a rotation of the frame? Yes, that rotates frame like that. Dy multiplied by 3. And finally, this is a pure rotation. That should come into the equation. Questions? So from here, I can work out By, and once I find By, I put it back in the second equation and find Ay. All right. Questions? Let's move on. (196). All right, so this is a tricky problem. So why this is tricky? All right, I want you to think about first before I explain. All right. I want you helping me answering this question. First, if I decide to make my envelope like that, anyone see this envelope? What is wrong with that free body diagram? If I only isolate dB, what is wrong with that? There is no known value. We only know that there are two unknowns, but we know the reaction at what n equal to reaction at another. So this is not solvable. If I take my envelope like this, how many releasing points are there? 2 releasing points. Both of them are pin, right? Both of them are pin. And for each pin, there will be 2 reactions. And my free body diagram, how many unknown would be there? 3, 4, 2 here, 2 there. How many reactions altogether? 4. And how many conditions I have to solve? I only have 3 conditions. 3 conditions, 4 unknowns. Is this solvable? It's not solvable. Unless you have a little piece of information which I gave you elsewhere. All right, let me put that in more, you can feel it better. So I just decided to make my envelope, my free body diagram like so. 2 releasing points. The first one is A, that's a pin. It has 2 reactions here. The second one is C. It has 2 reactions here. And then 1 external force here. So the problem is 1 unknown here, 2 unknown here, 3 unknown here, and 4 unknown here. How many conditions I have? The conditions I have is condition number 1, net forces x equal to 0, net forces, y equal to 0, net rotation. I only have 3 conditions, but 4 unknowns. This system is not solvable unless I can reduce one of the unknowns. All right, let's be a little bit smart. With C, yes, C is a pin support and it has 2 reactions. But what do we know about DC? DC, how DC is classified? Is this a 2-force member or 3-force member? What type of member is DC? 2-force. Do you remember the recipe I told you about the 2-force member? What is? With a 2-force member, the force has to be longitudinal. Otherwise, the member cannot be at equilibrium. Any 2-force member, whether this is a bar, whether this is a boomerang, if that is 2-force member, how do I know this is 2-force member? Because it has 2 exertion points, point D and C. These are the only places you apply force at them. If someone was pushing that in the middle, that was not a 2-force member. But in this usage, in this application, that's a 2-force. This is called the bar. This is called the link. This is called a 2-force member. A 2-force member here, DC, that should be treated as a 2-force member. And with the 2-force member, the only way the system, the member can be at equilibrium is the forces are axial. And what is the axis of this member? The axis of this member is to connect from point 1 to point 2. This is the axis, axial. If that was a boomerang, what was the axis of the member? Connecting from this point to this point, that was the axis, and then the forces would be like so. But in this case, because this is not bent, this is straight, the axis of the member is longitudinal. So with that longitudinal, I know the direction of force at C. So I don't have to worry about 2. Only let's just get rid of these 2 components and replace this with 1 single magnitude, because the direction I already know. What is the direction? The direction is direction of DC. DC is a 2-force member, so that I call this FDC. That's the only unknown. I know the angle. What is the angle? The angle is the very same as here. It's fully specified. Now let's come back and count the number of unknowns. So this is 4 kilonewton. This is FDC. That one I call this AX. This one I call this AY. So let's count this together. How many unknowns we have? 1, 2, 3. How many equations we have? 3 equations. 3 equations, 3 unknowns. So the problem is solvable. Does that make sense to everyone?
So for DC, Y is not FCD.
Why DC is not?
FCD. Y is not going to.
Yeah, FDC. Just think of the frame which I told you. You want to put a frame at the wall, and you want to apply forces at the top and bottom. No matter if the forces are equal, it fulfills the total sum of the forces horizontally, vertically. But because let us take this slide again, because some people came late. So here I explained that in the normal situation, if 2 forces, this is rigid body. So that potato is a rigid body. And if the forces are parallel, equal, opposite side, so this is F to the left, this is F to the right. And there is a distance between them, D. That the system from the net force point of view is at equilibrium. So the forces F minus F is 0. But from the rotation point of view is not at equilibrium, because we know that the rotation is M equal F times D. This is the distance. And then I told you what happens if I reduce D little by little. Suddenly, if I put D equal to 0, D equal to 0 mathematically gives 0 rotation. But you can imagine, When D is 0, it means I bring this force here and make that axially with that force. So here I have a two-force member. A two-force member can only be at equilibrium when the forces are opposing, equal, and coaxial. Either it tends to make the part shorter or longer. It never makes this bend. So a two-force member, then we just capsulize this one as a recipe. If an object is a two-force member, the forces have to be collinear. Otherwise, the member is not at equilibrium. And in this problem, if a car doesn't move, the tire doesn't move, the steering wheel doesn't move, the engine doesn't move, right? Very same thing here. The entire structure is at equilibrium. I can say, look, this one is at equilibrium, this one is at equilibrium, half of this one is at equilibrium, right? Makes sense? So that you can make a free body diagram here. This is a two-force member. And the only way this is at equilibrium is for two-force member. Forces are axial. Axial, opposite direction, equal size, equal magnitude. So that is how do we know the direction of FDC. Because this is action-reaction. The force which develops here is the same force which is applied at point C. So in a complex structure, you find the force in one part of the structure and transfer the very same force to the next part of the structure, and then transfer it to the next part. This is very common when we deal with the truss structures. You find the force here, and then the very same force which applies to that, through the pin, it is exerted to the next part of the structure. All right, so that is just we summarize the steps. We didn't go through the solution. But let me ask you, with this problem, if I want to be lazy and smart. So you try to be lazy in a good sense. It means you take only the minimum number of steps. You don't go unnecessary distance. So the minimum here, if I want to start with the rotational condition, with the third condition, so what would be the best point of rotation here? I want to apply the third equation, net rotation equal to 0. Which point is the best point of rotation, which by one single equation you can find, you can solve. A or C? C? Okay, if I take C, that would vanish FDC, that would vanish AX, and only you have AY. This is like a seesaw. AY multiplied by that distance is equal to 4 multiplied by that. And then that would tell me that AY is equal to 4 kilonewton, isn't it? Yes? So if I take, let's try that together. Net rotation with respect to the C equal to 0. And I assume that this is a positive direction of rotation, counterclockwise. So FDC is passing through point C. It doesn't make any rotation. And this one also passes through the C, doesn't make any rotation. And the only forces which make rotation is AY and 4 kilonewton. So AY rotation is minus AY times 1.5. And the rotation due to this one is negative, is minus 4 multiplied by 1.5 is equal to 0. And that tells me AY is equal to minus 4 kilonewton. It means my assumption of AY being upward should be rectified. Now AY is downward. And now that I find AY, for this, I can resolve that into two components. This is a 45 degrees, right? So that is, I can replace that by two vertical components. that is FDC square 2 by 2. That's cos and sine of, this is cos 45 degree, this is sine 45 degree, right? So I resolve that into two components. And now, then, if I write the first equation, that is AX is equal to minus root 2 by 2 FDC. I don't have a, this is two equation, but if I write the second equation is AY, which is minus 4 plus minus 4 plus root 2 by 2 FDC is equal to 0. And from here, FDC is 8 times 2 divided by root 2. Yeah, I want you to be more, making more attention to how free body diagram should be chosen, which equation, how the point of rotation be chosen to help. And then this is just by practice. The more practice we do, so let's go to page 198. Four 11. Okay, can I ask everyone to grab a piece of paper and try this one first yourself, and then we solve that together. All right, I'm trying to help you finding the point in this problem. and that is by asking question. Can you tell me two different ways of making free body diagram? Can you tell me envelopes for free body diagram? Just don't let the labels. We only have two labels, A and B, but believe me, there are two ways of making envelopes. So can you tell me what are the envelopes I can choose for free body diagram? AB is one envelope, and that's not the only one. Actually, there are three envelopes. One envelope is AB, one envelope is that rocker. The rocker has one end as a roller, the other end as a hinge. So if I just magnify that one, so what I'm trying to say is, look, I could make an envelope like so. That envelope is cutting through B and is cutting through the roller surface. If I want to make a free body diagram of that, let me draw you an enlarged view of this one. So this is B. That B has two reactions because it's a pin. But the other end, the sliding direction is like so, and normal to that is like so. So this becomes a three-force member. A three-force member. How a three-force member can be at equilibrium? The forces should be concurrent. They should collide at one single point. Yes. These are their assumption. Later on, with the numbers, if you get negative, positive, you correct them. But I mean, do we need to? Well, if I start with AB, that might not be solvable for the very same reason. Because if I start at AB, A is pin, it requires two reaction, and B also is a pin that requires two reaction. So how many unknowns are here? 4. How many conditions? 3. So that is not solvable. How can I solve? I mean, well, I need to just have a look at the rocker itself. Rocker, what type of member is it? Is it a two-force member or two-force member? So I know with B, it has one exertion point here, one exertion point here, right? So the rocker itself, that can be regarded as a two-force member. And how do I find the axis of this one? I connect from the first insertion point, which is here, to the second insertion point. That's the axis of the part. So with these two force member, I know the force has to be in that direction. So I get rid of these two forces and replace that with one single force, either this way or that way. I mean, you can make an assumption, later finding the right direction. If you are very experienced, at the beginning, at the onset, you could pick the right direction for that force. But even if you just make an assumption, it's not a big deal. Later, it would rectify itself. So here, I call this AX, AY. And this one I call magnitude of the B. And then the direction, so this direction is what? (30°), right? And now I managed to reduce that into 3 unknowns. 1, 2, 3. 3 equations. Now it's solvable. Without knowing that the rocker is a two-force member, the problem was not solvable. And my free body diagram is not complete because I forgot to include 4 kilonewton right here. Now it's complete. And with this new free body diagram, what is the best point of rotation? I can start with the condition of rotation, can't I? Yes, yes. All right. So B, let's isolate B from the universe. How many separation points are there? If I zoom in here, and I want to make an envelope, release this part, I have to release that from B, I have to release that from that roller contact. So in other words, this would be released from here, would be released from here. And what is my rigid body? Rigid body is this one, right? So no matter what is the shape of the rigid body, if that is a two-force member, that's how you find. I mean, I mentioned that some two-force member could be like a boomerang. This is one insertion point, one insertion point. So here, I don't care about this axis or that axis. So all it matters is connecting from here to there. And now I know the forces are either making that in tension or making that in compression. But in either way, the forces have the same axis. All right. So let's do the same thing here. One point is here, one point is here. If I connect these 2 points, that would be the axis of the member, right? If that is the axis of the member, with this little free body diagram, the forces are either pulling that apart or pushing that together. But in both cases, that's the direction of forces. That's the axis of the forces. So action, reaction. If this force is acting at B to the rocker, the very same force with the opposite direction would be applied to the beam, the horizontal member. So when I isolate the beam itself, I put the same force in the opposite direction. Third law of the Newton, action, reaction. The force which is acting on the beam shape here, same magnitude, opposite direction applied to the adjacent member, which is AB. So we transfer the force from this to next member. And now we try to solve that free body diagram. So still, do you want me to explain the free body diagram? Or is that, don't be shy. I'll try different wording. Maybe I can explain better. You want more explain again? Okay. All right. So this is the case in many situations. You have to deal not with one single rigid body, with several rigid bodies. What do we call this? We call this a composite structure, compound structure. Compound structure means my structure is made of many rigid parts. 2 rigid parts, 3 rigid parts. So this is an example. Here, how many rigid bodies are here? Nguyen, how many rigid parts are here? No, AB is one rigid body, and that rocker is a second rigid body. Let me take you to the previous example. Where did I put it? Here, how many rigid bodies are there? 2. One is the beam, one is the rope, right? Let me take you to another example. So the problem, this one, 4-2. How many rigid bodies are there? 2. A, B, and DC, right? So when there are a complex structure like this one, you have choices of making free body diagram. Free body diagram is just in your mind. I can make my envelope just to confine AB. In that case, I have to release it from C, release it from A. I can choose to have my envelope around DC, then I have to release D, I have to release C, right? Or I can choose to have my two rigid bodies together, this one, that one. So my envelope would be like that. If I take both of them together, then I have to release this from A from B. And C, we don't touch the devil. We leave it as it is. So once we don't cut it, don't worry about the internal forces. You only expose the forces when you release them. If I'm keeping C to the AB, that force, I don't include that in rigid body, in the free body diagram. Very same thing here. That is a composite member. If I decide to have my free body diagram to release from A and from this little point at the bottom, then we don't worry about the force at the pin because we kept two of them together. But if I decide to only take my envelope, including this one, that is a two force member. One rigid body with two force. If I take it like that, this is one rigid body with more than two force. If I take my rigid body to a stick, if I take my free body to keep two rigid bodies together, I have to release it from A, I have to release it from the inclined surface. If I release it from AB, my free body diagram, force at A, force at B should be included. So the problem, if I make free body diagram by releasing B, then there will be two, because this is hinge, B is hinge. Hinge, hinge, that makes four unknowns. It's not solvable. So the trick is just you, in the previous step, just a preliminary step, you just make a free body diagram of that. From that free body diagram, all you know is the reaction of B. You know the direction, you don't know the magnitude. So that piece of knowledge, you bring that to this free body diagram. You say, okay, instead of putting two forces, I only put the magnitude, the direction, I know what the direction is. And that makes the problem solvable. Otherwise, it's not solvable. All right, so the next thing is, I mentioned there are three conditions here. Can we go through the conditions together? One condition is net translation is 0. Second condition is net translation vertically is 0. And the third one is net rotation is equal to 0. And when I say three conditions, don't feel obligated you have to follow these orders, 1, 2, 3. Maybe you can start with 3. From problem to problem, which condition you start with, that is not the same. Here, can I start with the third equation? Who can tell me if I want to start with the third condition, how can I apply it to give me something solvable? With respect to the B, if I take it with respect to the B, let's see what happens. Yes, either A or B could be the good starting point. If I take it at B, that would vanish rotation of B, that would vanish rotation of AX. Only the rotation of AY comes into equation. So that becomes negative AY multiplied by 6 plus 2, 8, plus, or that is plus, yes, plus 4 times 2 equal to 0. And from here I find AY, correct? Now, at the same time, if I take rotation with respect to the A equal to 0, right? Still, I'm using the condition of rotation twice. It's not, this is a mix and match. Three conditions. You could have two rotations, one translation. You could have two translation, one rotation. So let me try the rotation condition twice. If I want to use it twice, with the second one, I write net rotation with respect to the A equal to 0. Let's see what do we get. Net rotation with respect to the A equal to 0. That is AX rotation vanishes, AY rotation vanishes, and BX rotation vanishes. So that is only BY. So BY is B cos 30, sine 30, and that is this one. The distance is 6, the arm of rotation, and that makes a negative rotation. And then you have 4, which makes a negative rotation also.
So this one is A.
With respect to the A, AX, AY don't.
Sorry. This stands for B sine 30 is A. That's it.
Which is a 6 plus third. Right?
Yeah.
The distance
With
between
respect to the A,
4 and A is 6, and then distance between 4 and B is 2. So
well, I'm taking with respect to the A, right? So these two
Yes.
don't rotate. This one doesn't rotate. That one makes a negative rotation. That's a negative rotation. And what about this one?
No, sir.
no, it's the distance
From A to B is
to
A.
A is 8 meters, not 6.
Okay, yeah. Thank you for that. My mistake. Thank you. That is 8.
Yeah.
And then is minus 4 times 6. So from here, you easily can find B. So you found AY, you find B. How to find AX? You have B, just project this. So AX is plus AX plus whatever B you find from here multiplied by cos 30 is equal to 0. And from here you find AX. All right, today we just started with free body diagram. And this is just the beginning. Between now and end of semester, we keep developing free body diagram for different problems. All you need to know is free body diagram is your decision. This is like you're a surgeon. You go to the patient and decide, I want to do the dissection like so. I want to cut this part of the body, this part of the body. Why? Because we want to examine that part by itself. And that involves lots of decision making. You only can make decision making if you have prior knowledge. So the prior knowledge you need is, first, make sure you understand the support types. What is the difference between a cable? What is the difference between a roller, between a pin support, between a cantilever support, between a guided support? That's make sure you sum them. Second, with the free body diagram 2 dimension, you fulfill 3 conditions. Make sure your free body diagram only has 3 unknowns. If with one free body diagram you find more than 3, either the problem is not solvable, or you have to solve something else before approaching this free body diagram. And that being said, I think we continue with that in our tomorrow class. But before that, let me finish the attendance, please. Okay, Serich away, Natasha is here, Nguyen is here, and Chaisal away. Daniel, Daniel, all these sessions being recorded. If you need to watch them, you can watch them on Collaborate Ultra. Okay, so the one which you didn't see, Abdullah is away. Jonathan got a job. Jonathan put me as a referee, so he got the job. I made a positive referee for him. He got a job, so wishing him the best. I don't think we see him anymore in the class. Ahmad is here. Nigel is here. Barnaby is here. Flynn is here. Shah is here. Darcy here. And Porty here. All right. I'll be sitting in the student hub. That's my 2 hour consultation time between now and 12:30. Feel free to come and see me if you need any help with anything. All right. And like always, just email me. And just Flynn told me that Pearson was done last night. I'm going to extend the last assignment for a couple of days. You can do them again. All right. Any question? Thank you very much. I look forward to see you tomorrow.
I have a question about
Yes.
what
Yes. Yes.
page 106.
Yes. Yes. All right. So that is a two rigid. Take a seat if you want.
Can you go back to your notes again? I
Yes.
got
Yes.
confused what you mean.
Yeah. I'll go back to my notes. Just, let me extend this one. That was due yesterday, was it? That was the fourth. This one, right? Oh no, this one. This was due yesterday. So we make that available until 16th. Okay, hopefully that is fixed. And I'm not sure if I still have that slide. Maybe I erased this. So yeah, we can just bring this back down here. This one, no?
Yeah.
Okay, so that is a two rigid bodies together. One is the horizontal rigid body here, one is that link.
So like this point is the same. It
Yeah,
doesn't
this is
matter. I
one
thought
member.
it's-
This is one member. This is one member. So these
I
people
thought it's like
seem to be
3
waiting
points.
for the class. Can we go to the student hub instead?
Oh,
Yeah, can we
Are
go
you
there?
free tonight?
Yeah, yeah.
What time?
Between now and 12:30. I mean, student hub. We are in class now.
Yeah, I have class.
We have to empty this class because people are waiting. I, we can be in there for a few minutes. Just do it
Okay.
quick.
Yeah.
So this doesn't clash with your remaining class.